Today we're going to discuss Feynman diagrams, which are a more efficient way for calculating scattering amplitudes and also correlation functions. And so they're entirely equivalent to what we did over the last few lectures, but for most practical calculations, it's much simpler to instead use Feynman diagrams rather than directly using, for instance, Wick's theorem and Dyson's formula and the LSE reduction formula. So what we're going to do is we're going to basically work backwards. So over the last few lectures, we went from the scattering amplitudes to expectation values of time-ordered products of free fields. And so we'll trace that backwards and see how we can represent our results using Feynman diagrams. So we can start out with a simple example. So last time we saw how we can compute time-ordered products of free fields or fields in the interaction picture using Wick's theorem. And our result was that the time-ordered product was related to the normal ordered product of all possible contractions. And after we take the expectation value, only the fully contracted terms survive. So using that result, we can relate this time-ordered product to product of Feynman propagators. Remember, the contraction is equal to the Feynman propagator. So this is just equal to all possible, the sum of the products of Feynman propagators from 1 to 2 and 3 to 4. So that's one possible way we could contract the field. So we could contract, for instance, 1 with 2 and 3 with 4. We could also contract 1 with 3, 2 with 4, or 1 with 4 and 2 with 3. And so here our notation is that delta ij is the Feynman propagator from xi to xj. Okay. So we'll compute this using Wick's theorem. Let's represent our result graphically. This will be our first example of a Feynman diagram. So can represent each of the propagators by a line and each of the space-time points by a dot. So we can represent this as just a sum of these three diagrams. And note that I'm leaving the space-time points in the same place in each of the diagrams. That's a convenient way to tell that you've drawn all the diagrams. If you leave the space-time points in the same point, it's usually easier. Okay, so expectation values of interaction picture fields are always going to look like this. They'll just involve sums of products of Feynman propagators. So we can just represent them as diagrams like this. So to get something more interesting, we need to go one step backwards in our chain and figure out what the time-ordered product of the interacting fields are, or the Heisenberg picture fields, and see what the Feynman diagrams for those correlation functions look like. So recall our result from last time. Right. The two-point Green's function, two-point correlation function, so that those all mean the same thing, the two-point Green's function, two-point correlation function, or the expectation value of the time-ordered product of two fields. Those are all synonyms. So last time, we saw that we could write this just in terms of a ratio of time-ordered products of free fields with this exponential factor that came from Dyson's formula. And then the denominator was the same, just without the extra fields. The interaction.
We sort of went from calling them interacting fields, well, fields in the interacting picture, to calling them free fields.
That's right.
You said they behave the same. I'm not sure what you precisely mean by that.
What I mean by that is they evolve with the free Klein-Gordon Hamiltonian, time evolve, and their correlation functions are the same as those for the free Klein-Gordon field. That's what I meant by that. Okay. So let's see how we can represent this result in terms of Feynman diagrams. And I'll give this two-point function another name, g. Well, that's g of x1, x2. And to see how to represent this result using Feynman diagrams, it will be useful to consider a particular example. So for the remainder of the lecture, we'll just consider the example where the interaction Hamiltonian is just the integral of lambda over 4 factorial phi to the 4th of y. Okay, so
That's in the interaction picture, or?
So remember the interaction Hamiltonian in the Heisenberg Schrodinger picture and in the interaction picture all take the same functional form. So if it's in the interaction picture, I just need to put an interaction picture field here. Okay, so let's break this up. So let's first look at the numerator. And again, this result is exact, but to proceed further, we need to Taylor expand the exponential. And so that's where perturbation theory enters in. So let's do that and look at the first two terms in the numerator. So the numerator is, I can write this exponential. The first term is just 1. Then the next term we get is phi 1, phi 2, minus I from the exponential, with lambda over 4 factorial, integral d4y, phi 4y. And then this will be, so this is perturbative expansion, and we're neglecting terms of order lambda squared. Okay, so each of these terms we can represent using Feynman diagrams. So the first term there's nothing new. Just represent this as a Feynman diagram, one propagator from 1 to 2. The second term, though, is more interesting. We've got something new here. So let's look at the second term. And we can write this using Wick's theorem the only terms that will survive are the completely contracted terms. So there are two classes of possibilities here. So first we could contract phi1 with phi2, in which case we would get delta 1, 2 times the integral d4y, delta yy, delta yy. If we contract phi1 and phi2, we're forced to contract the phi y's among themselves. And then you could also get some terms where phi1 is contracted as one of the phi y's, and phi2 is contracted with one of the phi y's, and that leaves two phi y's to contract among themselves. I said classes of terms because there are several different ways we could contract the fields to end up with the same thing. So for instance, for this term, we could contract the 4 phi y's in 3 possible ways. So we could contract the first two, contract the first and the third, or the first and the fourth. And so there are three ways to get a term, to get this term. So we get a 3 here. And similarly, there are 12 ways to get a term like this. So there are 12 possible contractions that give us a term like this. So 1 we contract with any of the 4 y's, then there are 3 left over that we contract any of the contract phi 2 with, and then we're forced to contract the last 2 y's. So that's 4 times 3, which is 12 possible contractions. Okay. And we can write our result in terms of Feynman diagrams, and then we can try to figure out how we can go backwards. So this first term, we have a propagator from 1 to 2, and 2 propagators from y to y. So we can represent the first term as this Feynman diagram, and the second term has a propagator from 1 to y, from 2 to y, and from y to y. So we can represent this result as this. And the technique of Feynman diagrams is to, if we're interested in this expression, first we write down the diagrams, and then we get the expression. So let's, based on these examples, see if we can guess some rules for how we can go backwards from this picture to these expressions. Okay, so here, rules. So this is our first set of Feynman rules, which are a set of procedures from going backwards from diagrams to expressions. And we might be interested in several different quantities in field theory, so the simplest thing we might be interested in are position space correlation functions like g of x1 and x2. And the Feynman rules for the different quantities we're interested in will be slightly different, will be related, but we'll discuss several different versions of the Feynman rules over the course of the lecture. So it's important to have them distinguished in your mind. Okay. So the first rule is basically just how we determined which diagrams to draw. So for each line, we associated a Feynman propagator. For each propagator, we associate a line. So if we want to go backwards, we associate for each line, we write down a Feynman propagator from x, y. The second rule is for each vertex, we get a factor of minus I lambda times the integral over the position of that vertex. So we can see that just by looking at our examples here. So in these first order diagrams, we had one vertex, and they all came with the factor minus I lambda integral d4y. And that just comes about because the only way we have more than one field at the same point is if we expand the exponential. And every time we get more than one field at the same point, it also comes with an integral over the position of that field and a factor of minus I lambda. And we'll come back to the 4 factorial in a minute. And so this one came from the interaction Hamiltonian. So this rule depends on the interaction Hamiltonian. The third rule I'm going to write down is trivial for now, but just to help Tibber out, I'm going to write it down because it will change when you consider fields with spin. So for each external point, we get a factor of 1. So this is completely invisible now, but this will be important for fermions and gauge bosons. Or we'll get a non-trivial factor for each external point. And so using the first 3 rules, if we had the diagrams, we could go back and reconstruct the expressions apart from the overall numerical factor. And we computed the overall numerical factor using Wick's theorem. There is a different way to compute it that in practice is usually easier, which is to divide by the symmetry factor. And I'll explain the last rule in some more detail. Okay, so what do I mean by symmetry factor? Okay, so let's look at, say, the second diagram we considered there, this diagram. And so we saw that this has a coefficient of 12 over 4 factorial, which is 1/2. And this is 1 over what I'm calling the symmetry factor. So the symmetry factor of this diagram is 2. And in general, S is the number of possible ways to exchange components of the diagram without changing the diagram. And for this example, there is there's a symmetry factor of 2 can be explained by the fact that if we exchange the ends of this line, this internal line, if we say gave them some fictitious labels, say called one of them the blue and one the orange line, it doesn't matter whether we put the blue line on the right or the left. So it is a symmetry factor of 2. And in general, there are 3 types of symmetries to look for. So first is exchanging the 2 ends of an internal line. Second is exchanging 2 lines. And the last is exchanging 2 vertices. Okay. So let's look at the other example and see if we can figure out the symmetry factor here. Okay, so if we look at this other diagram, we can compute the symmetry factor as follows. So first of all, we can exchange the 2 ends of the upper line. So it gives us a factor of 2. Independently, we can exchange the 2 ends of the lower line. And finally, we can switch the 2 lines. So we can exchange which line we call the upper line and which line we call the lower line. Sure. So the first 2 comes from the ends, exchanging the ends of the upper line. The whole diagram. So there are no symmetries of this part of the diagram. So we get a factor of 2 from exchanging the ends of the upper line. A similar factor of 2 for exchanging the ends of the lower line. And a factor of 2 from exchanging the lines. So this gives us a symmetry factor of 8 for this diagram. There's no symmetry of this part of the diagram. We can't exchange these 2 ends of the lines because these are labeled with the space-time positions x1 and x2, which are different in general. So if we switch the 2 ends of the lines, we'd be changing the diagram. And so the overall factor is 1 over 8. That's what we computed using the symmetry factor method. And what we computed before using Wick's theorem was the numerical factor was 3 over 4 factorial. And so 3 over 4 factorial is, in fact, equal to 1 over 8. So we do get the same thing as we expected. And so this is really why we chose our interaction Hamiltonian to have a factor of 1 over 4 factorial. And that's something we basically always will do. We'll choose the coefficients in our interaction Hamiltonian so that counting symmetry factors will always give us the same result as using Wick's theorem. OK. So that's the numerator. So we've learned the Feynman rules. Let's look at the denominator and see what's going on there. So the denominator we can write in terms of Feynman diagrams as 1. So the denominator is just the expectation value of the time-ordered exponential. And the leading term is just 1. The next term has one vertex and no external fields. So there's only one possible diagram we can draw. It has one vertex and no external fields. So this is the only order lambda term. And at next order, we'll have two vertices, each of which has 4 field operators at that point and no external fields. So one way we can connect the lines to the vertices is like this. Just have 2 copies of this diagram. Alternatively, we could connect the 2 points y and z once, or we could connect them 4 times. And so all of these terms are order lambda squared. We could keep going. So this diagram is a diagram we've seen several times already. So first we saw it in the numerator. Now we see it in the first order term in the denominator, and we see it twice in the second order term in the denominator. And that's not an accident. Let's see if we can understand that, why we keep seeing the same diagram. So at least these first 3 terms, these 3 terms, look like they come from the exponential of this diagram. So here I mean the exponential of the diagram, not the exponential of 8. If I turned it the other way, it would look like the exponential of infinity. Neither are particularly good, but what I mean here is just the exponential of this diagram. You can write this as 1 plus 8 plus a half times this diagram squared, 1 over 3 factorial, times this diagram cubed, and so on. And let's compare the first 3 terms here to the first 3 terms here. So they're almost the same. What's different is here I've labeled the points at the vertex. And then this one here I haven't. And this one has a factor of 1/2. So we saw that the symmetry factor of this diagram was 8. The symmetry factor of this diagram here is going to be 8 times 8, which is the symmetry factor of each part of the diagram independently. Plus, we'll get another extra factor of 2 from the fact that we can exchange the vertices and relabel these internal vertices because we're just integrating over them. So this diagram has an extra symmetry factor of 2 compared to this diagram squared. And that's just accounted for by this factor of 1/2 here. So this term is actually the same as this term, including the numerical factors. And again, this is not an accident. We can, in fact, write all of the terms in the denominator as an exponential of some of the diagrams. And so let's see how that works. Okay, so write the denominator as follows. So first of all, let's denote set of all connected vacuum diagrams as set VI. So these are diagrams like this figure 8 diagram we've been talking about. Also, the other two diagrams we saw at second order when we expanded the denominator, but there are infinitely many others. And we can write a general term in the denominator as just some number of copies of each of these connected vacuum diagrams. So for instance, we might have ni factors of the ith vacuum diagram. And if we do, we need to include a factor of ni factorial for the same reason that we had the factor of a half here. This is just the extra, counting for the extra symmetry factor from exchanging the entire diagrams, extra copies of the entire diagram. And so we can also, in addition to just having multiple copies of the same vacuum diagram, we can have, in one term, we can have any number of copies of any of these diagrams. And each term is going to have this form, and it'll just be some number of copies of each of these connected vacuum diagrams. And so we can write all terms as just the sum over all sets of integers and I. So this is the sets of integers. So again, this equation is just saying that the denominator is the sum over all, each term in the denominator just contains some number of copies of each of these connected vacuum diagrams, and the whole denominator is just the sum over all possible combinations like that. So we can write this in another way. So we can also write this as the sum for n1. So we can have some number of copies of the first diagram, the figure 8 diagram. And if we multiply that by the sum over all over n2, where n2 is the number of the second type of diagram that we have. This is the same thing. So this is still just saying that we're summing over all possible ways to choose a number of each of these connected vacuum diagrams. And you can write this in a different way. It's just the product over I, the sum of ni, 1 over ni factorial, vi to the ni, which now we can see why we got this result here. This is just the exponential of this factor in parentheses is just the exponential of vi. And the product of exponentials is the exponential of the sum. So I can write this as the exponential of the sum over I of vi, which is the exponential of the sum of these diagrams.
These things from you or not?
Yes, so
They can multiply it like,
these are, well, they're just integrals.
okay.
So the integrals over complex numbers. Yeah, we haven't worried about whether or not they converge, but they're just integrals. All right, so that's the denominator. We saw a very similar term, one of these connected vacuum diagrams in the numerator, too. And again, that's not an accident. Let's try to consider a similar construction like we just did for the numerator. And we'll see, try to understand the role that the vacuum diagrams play in the numerator as well. And we'll see that it works out very similarly to what we just did. So you can let Ci be the connected diagrams to two external points. If we're interested in just the two-point Green's function. So this is a diagram like this. This one. A diagram like this. And so on. And in terms of these connected two-point diagrams and the connected vacuum diagrams, we can write the numerator as follows. So the numerator is, so for one term in the numerator, we can have one of the connected diagrams with two external points. And then any number of copies of the vacuum diagrams, of each of the vacuum diagrams. So a general term will have some product over I of one connected diagram with two external points and some number of connected vacuum diagrams. And then the numerator is just the sum over all such terms. So we have the sum over j, and as before, the sum over ni. And we can then just pull out this factor Cj. The sums and products are independent of j. So we can write this as the sum over j of Cj times basically what we had before. The sum over ni, product over I, over ni factorial, the I to the ni, which is just sum over j, Cj times the exponential that we had before, the exponential of the sum of the connected vacuum diagrams. And so in the Green's function, if we take the ratio of the numerator with the denominator, these vacuum diagrams cancel out. So nothing in this derivation really required that we're just looking at the two-point function. So in general, we have that omega t phi 1 up to phi n, omega is equal to the sum of all diagrams with n external points and no vacuum diagrams. So vacuum diagrams cancel.
So that thing could be like divergent. Just because it cancels, we are okay.
Yes.
Okay.
Yes. So yeah, we are not worrying about whether or not it's finite, and it usually won't be. So. Okay. So now we know how to compute using Feynman diagrams an endpoint function. So if we're interested in computing an endpoint function at some order in the coupling constant, we just draw all diagrams with n external points and however many vertices we want, corresponding to the number of factors of the coupling constant we have, excluding all vacuum diagrams. And then we can directly write down the analytic expressions corresponding to those diagrams using the Feynman diagrams, Feynman rules that I just erased. So we can compute these correlation functions. So we've gone halfway back in our quest to understand how to write down the Feynman diagrams and use Feynman diagrams to compute scattering amplitudes. So now we know that the LSZ formula relates scattering amplitudes to correlation functions. So let's next try to understand which Feynman diagrams we should write down when we're considering scattering amplitudes, and how we can write down a set of Feynman rules that will, after we've drawn the Feynman diagrams for a scattering amplitude, how we can then write down the analytic expression. Okay, so as you recall, our LSZ reduction formula tells us that FSI is equal to, for now, let's restrict to 2 to 2 scattering. So 2 to 2. So we've got I to the 4th, then 4 integrals over 4 positions. And then factor e to the I e dot x1 similarly for x2, if x1 and x2 are the initial particles, and then we have a plus sign here and a minus sign for the final particles. And then we've got a product of Klein-Gordon operators. One for each particle. So they're all the same particle. And finally, our 4-point correlation function. Okay. So we've already seen how to represent this result in terms of Feynman diagrams. And what we've seen is that at leading order, we have this correlation function. It's just equal to sum of these three diagrams. And we higher order corrections. And now that we're talking about scattering amplitudes, it's useful to draw an arrow of time on our Feynman diagrams. So I'm going to have time go upwards. So in the LSE reduction formula, the sign in the exponent depends on whether the particles are incoming or outgoing. So it's useful to distinguish which particles are incoming and which particles are outgoing. So I'll always draw time going upwards. Some people like to draw time going to the right. So either one is fine as long as they're consistent. Okay, so now we know what the analytic expressions for these diagrams are. So we've already learned that. So let's see what the LSE reduction formula tells us about how these diagrams contribute to the scattering amplitude. So let's look at these diagrams one at a time. So this first diagram is delta 1, 3, delta 2, 4. And let's just pull out the expression is rather long, so let's just look at pieces of it at a time. So we're going to have a Feynman propagator from 1 to 3. So let's just pull out the parts of the LSE formula, or some of the parts that care about x1 and x3. So we'll have a Klein-Gordon operator with respect to x1 and a Klein-Gordon operator with respect to x3 acting on the Feynman propagator from x1 to x3. And let's just give this a name so I don't have to keep writing it. Call this F. And then also in the LSE reduction formula, we have we're basically Fourier transforming F. So we've got an integral d4 x1, d4 x3, e to the I p dot x1 minus p3 dot x3, acting on f. And let's try to compute this part. So we can do a change of variables. So if we do the change of variables, so do the change of variables. x13 is x1 plus x3. X bar 13 is x1 minus x3. And similarly for the p's, but I'll put in a half. And if we do that change of variables, what we get is a factor of a half from the Jacobian. Integral d4 x13, d4 x bar 13, e to the I p bar 13 dot x13 plus p13 dot x bar 13. And f only depends on x bar 13, which is why we're doing a change of variables like this. And so after we've done this change of variables, we are now just doing a Fourier transform of f. So we can write f in terms of its Fourier transform as, so if we do this integral, we just get this. We're still left with e to the I p bar 13 dot x13. Now we've got the Fourier transform of f, which now depends on p13. F tilde is now independent of x3. So the second integral is just going to give us the delta function. So it'll give us a delta of p3 bar, which we can rewrite in terms of a delta of p1 minus p3. And we'll kill the one factor of a half out front. So we're left with delta p1 minus p3. And then we've got f tilde back in terms of original coordinates of p1 plus p3 over 2. Okay. All right, so this is basically half of the LSE reduction formula for this term. The other term works identically. So you can see that the contribution to the scattering amplitude from this term, is proportional to a delta which sets P1 equal to P3 and a delta which sets P2 equal to P4. So contribution from this Feynman diagram does not correspond to scattering. Basically, if final particle 3 has exactly the same momentum and it's the same type of particle as P1, and similarly for P2 and P4, then no scattering has occurred. So this Feynman diagram only contributes to the trivial part of the S matrix. So remember, we wrote the S matrix as 1 plus IT, where T was the transfer matrix, which contained all the interesting physics. So this is not part of the transfer matrix. It corresponds to no scattering. So this diagram is not very interesting, and exactly the same logic for this diagram, cross diagram. So what about this diagram? This diagram is even worse. So we have that for the equals diagram, the amplitude is proportional to a delta that sets P1 equal to minus P2 and P3 equal to minus P4. But these are massive particles. So the zeroth component of P1 is greater than M. And similarly for the zeroth component of P2. So the sum of these two is greater than or equal to the mass, which is not 0. It's greater than 0. So these deltas are never satisfied. So because our initial and final particles have a mass and therefore have a positive energy in any reference frame. So this is so this contribution vanishes. It's proportional to a delta function, whose argument is never 0. So leading order, we've got 1 0 contribution and 2 trivial contributions. And the same argument works basically for some of the diagrams beyond leading order. So if we considered a diagram, say like this, which had a vertex, but there were no interactions, or the diagram is disconnected, so there's no interactions between all 4 of the particles. This diagram will also be proportional to the same delta function, delta P1 minus P3 and P2 minus P4. So this diagram, or diagram like this, any diagram that's disconnected will have the wrong delta functions. So these will not correspond to scattering. So the first lesson we've learned is that only fully connected diagrams correspond and contribute, that's probably a better word, contribute to N to M scattering. It's possible, if we're interested in, say, 4 to 4 scattering, we could have a disconnected diagram that corresponds to 2 independent 2 to 2 scatterings. Again, we wouldn't say that's not interesting if we're interested in 4 to 4 scattering. So only the fully connected diagrams where there's a path we can take from any external point to any other external point contribute to N-to-M scattering. So that tells us that the first interesting diagram occurs at order lambda.
Are there ever actually situations where n is like greater than 2? Any useful description of anything?
N greater than 2 is,
Like, do you think that like 3-body
yeah, I can't think of any examples. M greater than 2 is often interesting. Okay, so the first interesting diagram is this one. And we can write down, using the Feynman diagrams from earlier, Feynman rules for earlier, the expression for the correlation function corresponding to this diagram. And we just get this. We've got one vertex, so we have one factor minus I lambda through D4. And we have propagators from each of the external points to y. And there's no symmetry factor, because the external points are all different in general. So the contribution to the scattering amplitude from this diagram is using the fact that the Feynman propagator is a Green's function, so it satisfies this equation. There's a minus I, but it's still a Green's function. So what we get is we can apply the Klein-Gordon operators to each of the propagators, and then use the x1 through x4 integrals to get rid of the delta functions. And then what we're left with is just this integral over d4y and the exponential factor, where now all of the xi's are set equal to y. And this is an integral we can do. So what we just get is minus I lambda 2 pi to the 4th delta 4 of P1 plus P2 minus P3 minus P4. And so we just get minus I lambda times an overall momentum-conserving delta function. And such a delta function occurs in all completely connected diagrams. So I mentioned a few lectures ago, what we usually do is we pull out the interesting contribution to the completely connected scattering amplitudes and call that the matrix element, or I times the matrix element. So what we found is that our first matrix element is just minus lambda. OK, so let's go to the next order and see what happens. So one diagram we can draw at the next order is this diagram. And so this diagram has two vertices. So there are two factors of minus I lambda. An integral over the position of both of the interaction vertices. Then we have Feynman propagators from 1 to y, from 3 to y, from 4 to y, from 2 to z, from z to z, and from y to z. And the last step is to figure out the symmetry factor. So the only possible thing we can do here is exchange the two ends of this line from z to z. So we get a symmetry factor of 2. So again, I've just applied the position space Feynman rules for the correlation functions to get this result. Okay. So
why we had two lambdas? You said because we had two vertices?
That's right. So this comes from the second order expansion of the exponential of minus I times the integral of the interaction Hamiltonian. And so so our interaction Hamiltonian was the integral of lambda over 4 factorial times the integral of phi 4. And so every time we have 4 fields at the same point,
Okay.
it also comes with a factor of minus I lambda and an integral. So we had the minus I came from the fact it was the exponential's integral had a minus I in it, and it also had an integral with respect to time that turned this d3y into a d4y. Okay, so let's try to compute this in the same way we did the leading order term. Compute the contribution to the scattering amplitude from this diagram. And so up front, we just have this factor. Keep the integrals. And all of those Feynman propagators, after we plug into the LSE formula and act with the Klein-Gordon operators on them, we just get delta functions. We can do those delta function integrals using the x1 through x4 integrals in the same way as we did before. So we're just left with is the exponential factors. This time, some of the x's are set to y, and one of them is set to bz. And also, this time, we have 2 Feynman propagators left over. Okay, so this comes just from doing xi integrals function. Okay, so here it will be useful to use our result from one of the first lectures where we computed the Feynman propagator, and we found it's just integral d4k, 2 pi to the fourth, I over k squared minus m squared plus I epsilon to the I k y minus z. This is a result from the first lectures. And if we plug this into our expression for the scattering amplitude and do the y and z integrals, what we get is this expression. And then we have delta functions that come from doing the x and y integrals. Here we've got p1 plus k minus p3 minus p4. Okay, so notice we've got a k in here. That just comes from this exponential factor when we plug in for the Feynman propagator delta yz. And delta zz doesn't contribute a factor because it's z minus z in the exponent. This is what we get. From doing the y and z integrals. And now we can try to do, say, the k integral. Let's try to do the k integral using this second delta function. And if we do that, what we get, I won't write the whole thing, but just integral d4k delta p2 minus k of 1 over k squared minus m squared plus I epsilon. So we do this integral. This just sets k equal to p2. So we get 1 over p2 squared minus m squared. So remember, this notation just means we take the limit. This is just a specification of the contour, or we could think about it as taking the limit epsilon goes to 0. So we just get 1 over p2 squared minus m squared, which, since p is an external particle, satisfies p2 squared equals m squared. So this is 1 over 0. That's bad. So we got a divergent contribution from this diagram.
Can you repeat what you said about delta ZZ not contribution?
Yes. So if we wrote down delta z, so it would be the same expression as we have here, except we would replace this y with a z. So we have the exponential then of 0. So delta zz is just going to be integral d4, I call it d4q over 2 pi to the fourth I over q squared minus m squared plus I epsilon.
So what part is contribution by delta YZ that is not contribution by delta?
So the reason that this k is in these delta functions is because there's a ky and a kz. Okay. So this is problematic. Got a divergent contribution from this diagram. And the resolution to this problem is that we shouldn't have even considered this diagram in the first place. And what we should do is amputate. And so first of all, what does amputation mean? And then a brief word about why we do it. Okay, so amputation. This means that if we have some diagram with some external points, could be any diagram. That could be interesting things going on the legs. We could have things like this. And what amputation means is if we have some diagram that has corrections or loops on the external legs, when we amputate the diagram, we just, on each external leg, we cut the leg after all loop corrections. So if there were several loop corrections on one leg, we would go past all of the corrections and then amputate, so just remove any corrections and then replace that with the diagram with all the loop corrections on the legs removed. So what we don't want to do is if we have a diagram that has, let's say we have a diagram like this, and we wanted to amputate it. So if we amputate this diagram, there's only one leg we can cut. So this diagram will give us a contribution like this. So amputation doesn't remove all possible loops or interactions between the particles. In fact, that's exactly what you want to preserve when you're amputating a diagram. So when you amputate a diagram, you just remove any corrections to the external legs. And the reason for that, which we'll discuss more when we discuss renormalization in QFD2, is that single particle state in the interacting theory is not the same as an interacting as a single particle state. In the free theory. And so one particle state can be represented in terms of Feynman diagrams as the free propagator plus loop corrections. And so we shouldn't consider this diagram because this diagram is just the same as that diagram with some corrections to the state of particle 2. And we'll come back to this point in a little more detail in QFD2. So let's summarize and see if we can guess what the Feynman rules are for the scattering amplitudes or matrix elements. And let's write down momentum space, Feynman rules, for the matrix element. So the first thing we see is that the matrix element is the sum of all completely connected and amputated diagrams. So they have to be completely connected so that they correspond to n-to-m scattering, and amputated so that we consider the correct initial and final states. And now let's see if we can write down the Feynman rules for this. So first of all, and I'll try to provide some justification for where these Feynman rules come from the Feynman rules we had before and the LSE reduction formula. Some of the details you'll work out in tutorial, or have more of a chance to convince yourself that where these rules come from in tutorial today. So the first rule is for each internal line, we get a factor of I over p squared minus m squared plus I epsilon. So there are two things worth commenting on. So one is that it's only for the internal lines. So in the LSE reduction formula, we had Klein-Gordon operators, which basically remove the propagators to the external points. So all that's left over are the Feynman propagators for the internal lines. And the second point is that we're computing the matrix element in momentum space. So here what we have is the Fourier transform of the Feynman propagator.
By internal line, you mean a line that has both endpoints, are internal? Like if I have
That's right.
Z is 3 to Y, that's considered. Okay, yeah.
That's right. So, for instance, the Y to Z and Z to Z are the two internal propagators here. The second rule is for each vertex, we get a factor minus I lambda. In position space, we also had an integral here. So we've used those position integrals when we've gone to momentum space to basically do Fourier transforms. So in momentum space, there are no integrals left over. And again, this rule is specific to phi-4 theory. So which vertices are allowed and what the Feynman rules for the vertices are depend on the theory, just like they did in the position space version where the vertex rule came from the form of the interaction Hamiltonian that we wrote down. Our third rule is carried over from, it's related to rule 1 and rule 3 from before. And it's for each external line. We get a factor of 1. And the reason it's even worth writing this down is this will change again for fermions and gauge bosons. Tibor will tell you all about that. And so again, the reason for the difference between rule 1 and rule 3 is that the LSE reduction formula has Klein-Gordon operators, which kill the propagators for the external particles. Rule 4 is that we should impose momentum conservation. At each vertex. And we saw an example of how that works. So here if we look at these delta functions, what these delta functions are telling us is that in this diagram, if we say we've got momentum, we can draw this diagram again. If we got momentum P1 going here, P2, P3 going out here, P4 going out here, P1, 2 going here, and K going here, and Q, I called it, right there. And these delta functions tell us that P2 is equal to K, and that P1 plus K is equal to P3 plus P4. So that's telling us we have momentum conservation at both of the vertices. Q doesn't enter because Q both enters and leaves this vertex. So these momentum conserving delta functions tell us that we should impose momentum conservation at each vertex. Rule 5 is divide by the symmetry factor. So this, again, is just left over from our Feynman rules for the correlation functions in position space. Rule 6 is, the final rule is we should integrate over any undetermined momenta. So here, if we just, in this example, if we just, we could do the K1 integral using the other delta function, this one. And that would just set K equal to P3 plus P4 minus P1. We'd be left over with one integral we couldn't do using a delta function. And that's because we have one loop. So in general, for every loop we have, we'll be left over with one momentum that we can't fix using momentum conservation. And so those leftover undetermined momenta should be integrated over. And so just in the, I guess I'm over time, but in tutorial today, we'll look at some examples of how to apply this.
For rule 3, what is this branching thing on the left mean?
So this is just the same notation that I was trying to use when I wrote the one particle. So this is just however it connects to the rest of the diagram. This just means that, yeah, it's just supposed to be an external line that can connect to the rest of the diagram in any possible way.
Not an arrow.
Not an arrow, no. So notice that I have indicated the flow of momentum using arrows that are not on the lines. So there are no charges in phi-4 theory, but usually, so over here again, I've used the arrows next to the diagram to indicate the flow of momentum. We always, it's traditional to reserve arrows on the lines to indicate the flow of charge. So when we're dealing with, say, a complex scalar field or charged particles of any kind, then we can indicate the flow of charge by arrows on the line. So it's useful to distinguish the notations. Yes?
The argument why do we perform the amputation? Like, what are we saying with that? I don't understand that drawing and why it's directed to single particle state.
Okay, so the picture we have is that we have some well-separated particles in the far past and the far future, and they're interacting for some short time. So that's approximately true, but particles can interact with themselves too. So it's not quite true that they only interact with each other at some time. If you have a particle that's separated from all other particles, there's still virtual particles that it can interact with. And that's basically what those diagrams are meant to represent, is like interaction, the one particle state, that the well-isolated particle is not actually well-isolated in quantum field theory. It still interacts with virtual particles. And we need to take that into account. And we'll see how to do that when we discuss renormalization. So.
I'm sure
Because that still is the one particle state. That's the best you can do in quantum field theory. You can never have a particle that's not going to interact with anything for a long period of time that can interact with virtual particles. That's the hand-waving explanation. We'll see how it works in quantitative detail in QFT2. All right. So that's all for today. I'll see you this afternoon.